Up, we have Jayadev. From the bootcamp, our experience was that for Jayadev to hear us well, we need to speak into this mic. So if you have a question, try to put up your hand or yell for me if I don't see you, and I'll run to you with this mic. With that, Jayadev, it looks like you're set up. Can we test your audio? Can we hear you?
Yes. Can you hear me?
We can hear you. That's excellent. Okay. Sorry, we're running a little bit behind time. Jayadev, if you want to take until 10 past the hour.
So hopefully I won't take more than 23 minutes. That was the instruction. Let's see how it goes.
Thanks. That's awesome. Jayadev Acharya is joining us from Cornell. Take it over, Jayadev.
Okay. So first I would like to thank Sam, Lenka, and Afonso for inviting me to attend this workshop and for the opportunity to speak. And I hope to be at Simon's again, hopefully in person and hopefully soon. And before I start, I would like to apologize for the paper not being online yet. And we hope to put it up before the talk, but clearly my estimation didn't account for robustness. And we hope to have the paper online before the end of the week. And if you would like a draft of the paper, please send me an email and I'll send a draft. Okay, so this is the joint work with Ayush Jain, who is a student at UC San Diego, and Gautam Kamath, my long-term collaborator, and same with Ananda Tirtha Suresh and Huanyu Zhang, who is at Facebook Research. So here is a brief outline of the talk. So we'll start with the problem formulation. I'll talk about related works and then present our results and sketch of the proof, and we'll finally conclude. So what's the setup? It's a very simple problem. We have an addition graph over n nodes. And what's an addition graph? The probability that an edge between node I and j exists, it's small p, independent of each other. So it took me some time to draw this, and I know for this audience, it's probably not needed, but I'll still go through with it. So for example, this edge between 1 and 3 exists, edge between 1 and 5 exists, and so on, you get this graph. And the question is just, given this graph, what is p? Okay, that's the whole question. So this is a simple question, so there should be a simple answer. So if d sub j denotes the degree of node j, then you can come up with the estimator, which is, we call it the mean estimator, which is just counting the fraction of edges that are present. So it's the empirical estimator for p. And similarly, you can come up with a median estimator, which basically looks at the degrees of all the nodes and looks at the median of this degree and normalizes it appropriately. And that's the median estimator. And it's not hard to show that for both of these estimators, your estimate for the true value of p will be about a constant factor of square root of p times 1 minus p divided by n, because the distribution of number of edges itself is binomial n choose 2 comma p. Okay, so this is the basic setting, but now we want to ask what happens if you have corruptions. So what's the setting? You have an adversary A. What it does is it looks at the graph, the true underlying graph generated by G and P, and it picks a subset of nodes of a particular size, gamma n. So we'll say that a gamma fraction of the nodes are corrupted. And once it chooses this set of nodes, it can now change the neighborhood of B as it likes. So it can rewire all the connections to the nodes in B. And then we observe the resulting graph, which we call as A of G. Okay. So in the same picture as before, let's say the nodes 2 and 6 are corrupted. Then what the adversary can do is maybe it can delete the node, the edge between 2 and 7, and it can come up with a bunch of connections to either 2 or 6, like this. And the question is still the same. Given this graph, estimate p. So it's a very simple univariate estimation problem. You're given this graph, what is the value of p? Okay. If there are any questions, please feel free to.
Can I ask something?
Yes.
Is gamma constant?
We'll look at various ranges of gamma.
Okay, thank you very much.
Gamma can be anything between, gamma is, for our results, until now, we assume gamma is less than constant, less than 1 by 60 or so for our results to go through.
Thank you.
But gamma can be between anything between 0 and let's say 1 by 60. Okay. So now also we just have one univariate parameter to track. That's it. So what can we say? So this is a task of a robust estimation. And of course, there is a long history for robust estimation, including pioneering works in robust statistics by Donohoe, Hampel, Huber, Rousseau, and Tukey. And more recently, there has been a flurry of work in CS and stats communities on computationally efficient estimation of multivariate parameters. Okay, because, starting with the work of Lai, Rao, Vempala, and Diakonikolas, Kane, Kamath, Lee, Moitra, and Stewart. Okay, I did it. And then there are related works on robust estimation of discrete distributions from batches by Chow and Valiant, and then by Chen Li and Moitra, and Jan and Orlitsky. And robust estimation on graphs has been looked at by Tsai and Low on for robust community detection, where again you have corruptions of various nodes, and this is a related task to our problem. And the problem of estimating properties of graphs under differential privacy was studied by Borgs, Chayes, Smith, and Zadik in 2018, and then a follow-up work of Silfon and Ullman actually looked at exactly estimating the parameter of an addition graph under node differential privacy. Although in terms of technical contributions or technical content, we couldn't find a connection between their techniques and what we will come up with. Okay, so again, our problem is very simple, just one parameter to estimate. Okay, so we may think, okay, so what should we do? Let's try to see what happens for simple estimators, right? So if you just use the estimators as before, then it's not hard to show that for both the mean and the median estimators, the error that you incur is the second term here is the non-robust term, and you will incur an additional gamma error in your estimate. And the easiest way to think of it is you have these gamma n nodes, just connect them to everything else. So that gives rise to about gamma n square edges, giving you a gamma factor in the estimator. Okay, so maybe this is bad, but maybe when we are doing it, we are probably adding these nodes, adding these edges, which are making some of the degrees very high or very low. So what about we just prune some of these nodes and then do this estimate? So what one can do is first remove a fraction of C gamma nodes with the highest and smallest degrees. So C can be anything between 0 and 1 over gamma. And after you do this, just output the median or mean of the remaining subgraph. So what one can show is if you do this pruning algorithm, then apply the median, you will again incur, there exists an adversary such that there is still a gamma error that you will incur on top of the non-robust estimation. And if you do prune then median, prune then mean instead of prune then median, you'll incur an additional loss of gamma square. And both of these are actually typed. Okay. So now the question becomes, is this dependence on polynomial dependence on gamma necessary, or can we do something better? So that's the question that we'll try to answer. So our main result is the following. And okay, this looks a little complicated. I'll try to parse it through very quickly. So we show that there is an algorithm whose error is a combination of these three terms. The first term is the non-robust error, and the second two terms basically take care of the robustness. Okay, and our algorithm, I'll make a few comments on this exact error rate in this slide later on. And our algorithm runs in time gamma n cube plus n to the 2.5. We believe the n to the 2.5 can become n square by making the algorithm more complicated. Okay, so if we look at these error terms, and let's, for the sake of this talk, to make some of the results a little more digestible, let's assume that we are not in the extremely sparse regime. So we assume that P is at least 1 over n, so that the graph has more than order n edges. And P is less than 1 minus 1 over n. This is just for simplicity. And let's assume that gamma is at least 1 over root n. Why? Because if gamma is less than 1 over root n, then you can see that the non-robust term is going to dominate and robustness has no effect. So until gamma equal to 1 over root n, you're not going to pay any penalty beyond a non-robust estimation. Okay, so once we assume just these two things, that gamma is at least 1 over root n. So at least 1 over root n of the nodes are corrupted, and P is not too small, not too big. Then just the middle term is going to dominate, and we can write it in the following way. So the error in our estimator, the upper bound is the non-robust error, which is square root of P times 1 minus P divided by n times gamma square root n. Okay, so in particular, if let's say gamma is a constant, then you are going to incur an additional error of a factor of square root n beyond what you did for the non-robust setting. Okay, so that's our main upper bound. And for the lower bound, we are going to show an almost matching lower bound. And again, I'm going to state it in this same regime that P is not too small, not too big, and gamma is at least something. And for that, for this, I'm going to define delta P gamma n to be just the term that we had, just our best error term. It's the exact same thing. I'm just writing it compactly. Okay, so this is the error lower bound that we want to prove. So our bound is our result is this. We can show that there exists an adversary such that if you give it a graph G distributed according to G and P, and a graph G prime distributed according to G n P plus delta, then the adversary can take these two graphs and make changes to both of them up to a gamma fraction, such that the resulting two graphs will have a small total variation distance. And once this happens, you cannot distinguish between the two graphs, and therefore you cannot estimate up to any accuracy better than delta. Okay, so that's the main upper and lower bound. And it turns out that our lower bound, in fact, can work even if we select a random set of nodes and corrupt them. Instead of looking at the entire graph and selecting the nodes dependent on the graph, we can select a random set of nodes a priori, and still these bounds cannot be beaten. Yeah, so both the upper and lower bounds are tight up to log factors. In fact, these are tight in all the terms, but again, as I said, for this presentation, we'll just look at, we'll just focus on this regime. Okay, so how do the upper bounds work? So it's going to be a two-step algorithm. The first will be a spectral algorithm that's going to output a coarse estimate p hat that doesn't have the gamma factor. So if we had this extra gamma factor in the first, in this term, we'll be done. So we'll first come up with a coarse estimate, and then a pre-processing step to get the gamma factor in. Okay, so how does it work? Our first observation is that large subsets of uncorrupted nodes are good. In other words, if I give you a large subset of nodes that are not corrupted, you can just take them, output their empirical mean, and that will match the bounds of our theorem. Okay, so let's look at some definitions. Let A denote the adjacency matrix of A of G of the graph that you have, and for a subset S, let A of S cross S denote the submatrix of the adjacency matrix restricted to S cross S. So it's basically the adjacency matrix of the subgraph restricted to S. And let P sub S denote the average density of this subgraph. So you take a set of S nodes, so S is a subset of N, and PS denotes the average density over this subgraph. Okay. And we are going to denote by A minus PS to be the adjacency matrix A of S cross S, and you then remove the mean from each of the entries. So you are left with a zero mean matrix. Okay. So now this is actually zero mean random matrix with some corruptions. And let's define F to be the set of uncorrupted nodes. Okay, so what we can observe is that simultaneously for all subgraphs of F, simultaneously for all subgraphs F prime of size at least n times 1 minus 18 gamma. So it's a large subgraph. The following two things hold. One is that the spectral norm of A minus PF. So you take this, take the subgraph over this F prime, over the nodes in F prime, and take their adjacency matrix, remove the mean. The spectral norm of the resulting matrix is small. And the second observation is that if you just take this subgraph on F prime and look at its empirical density, look at the density of the edges, that is a good estimate of P. That will actually give you back the main upper bound. So if you knew F prime, you're good. Okay, so that's observation 1. Now let's look at another observation that will tie in with this. It's we have the same setup. We have a subset S of nodes of size at least n times 1 minus 9 gamma. So it has both bad and good nodes. So both the corrupted and uncorrupted nodes. And the observation here is that if A minus PS, so you take the subgraph, the adjacency matrix of the subgraph induced over S and you remove the mean. If the spectral norm of this matrix is small, then the average density of this subgraph is a coarse estimate of P. Okay, so this is sort of the converse of the previous page. So you can take a subgraph, find its once you fix the subgraph from the graph, you can compute this matrix and figure out its spectral norm. And if it is small, then you have a coarse estimate. And the proof sketch is actually pretty simple. So you have the subgraph over S nodes. And S intersect F is large because F is a set of all good nodes, which is of size 1 minus gamma, and S is also of size at least n times 1 minus 9 gamma. So S intersect F is a large uncorrupted set, which means that the empirical density, which means that the density of S intersect F is close to P by the result in the previous slide. Which means that if the empirical, if the density of the entire graph S cross S is away from P, the remaining entries have to have a mean far from P. And once this happens, you have the adjacency matrix of this graph, of the subgraph over S. A big chunk of it has a mean of P and the remaining has a mean away from P. Using that, you can show a lower bound on the spectral norm. Okay. So this actually just gives us a coarse estimate of P using an inefficient algorithm. You can iterate over all large subsets and minimize the spectral norm. Okay, but we want to do it efficiently. So what we can do is this will be our main lemma to make the previous inefficient algorithm efficient. Suppose S is any subgraph of size at least n times 1 minus 9 gamma, and let V denote a normalized top eigenvector of A minus PS. Okay, so you take the top eigenvector of this matrix. And then our main lemma states that if the spectral norm of A minus PS is large, then this, so V is a normalized eigenvector, then the component of V along the bad nodes has to be at least a constant. So V is a unit vector, so V1 square, V2 square, and so on, which will add up to 1. So the contribution of V from the bad nodes is at least a constant. So now this gives us a simple way to try and prune these nodes out. So you start with the entire n nodes. At each time, you compute the top eigenvector of the current subgraph that you have. And then you sample I with probability Vi square. And by this main lemma, with at least a constant probability, you'll pick a bad node and you will delete it. It will keep repeating it. And doing this will give you a graph, will give you a subgraph that will imply a coarse estimate of P. And this is the main lemma that required some work, and I won't go through it in detail. I just don't have time. The step 2 is actually very simple because, so what the first step is doing, it's giving you a set, a subgraph S star, so that the density of S star P of S star is a coarse estimate of P. So without the gamma factor, it's good. Now the second step is actually pretty simple. You just take these nodes in S star, remove the top and bottom 3 gamma n nodes with the highest and lowest degrees, and you output the mean P hat of the remaining nodes. And we can show that up to log factors. This estimator is gives you the upper bound that we wanted. Okay, the remaining 4-5 minutes, I'll go through the lower bound and then people can ask questions. So let's recall our lower bound. Okay, this is too many questions. Okay, we wanted to prove this lower bound of gamma square root P 1 minus P divided by square root n. And we said that we'll show the existence of an adversary such that TV distance between the two induced graphs is small. So how do we prove lower bounds on graphs? We have to come up with some kind of coupling. So if we can convert a graph that's generated from G and P to a graph that's generated from G and P plus delta by changing at most gamma n nodes, then we are done. So how can we do that? Let's note that the degree distribution of nodes in G are binomial n minus 1 P. And the degree distribution of nodes in G prime are binomial n minus 1 and P plus delta, okay, just by definition. And the way that this delta is chosen, a little bit of computation can show that for the definition of delta from the previous slide, the TV distance between these two binomial distributions is at most gamma over 10. So in fact, if the degree distributions across nodes were independent of each other, then actually we are done, because now we look at each node and we convert each node independently of each other from GNP to GNP plus delta. And this will change at most n times gamma over 10 nodes in expectation, and that will give you a lower bound. But unfortunately, the node degrees are not independent. So in that case, what we do is to go to directed graphs, because the one nice property about directed graphs or directed addition graphs are the out degrees are all independent. So let dg of np denote directed addition graphs. Then the outgoing nodes are again binomial n minus 1p, and the degrees are all independent of each other now. So you pick a node, select each of the outgoing edges with probability p. And now, because the degrees are independent of each other, we can get a lower bound of delta p gamma n for estimating directed parameter p for directed graphs under gamma corruptions. And we can show that for any gamma, parameter estimation for the undirected addition graph is harder than estimating the directed version of the problem. And that gives us a lower bound. Okay, this is my last slide, I hope one time. So in conclusion, we asked a natural and simple question of estimation of a simple parameter estimation problem on graphs. Hopefully this gives us a new direction of problems to look at. And we gave almost optimal results for addition parameter estimation. And we have some ongoing works on stochastic block models that hopefully that I don't have time to talk about. And there are many other interesting directions. For example, what happens for other random graph models? How can we estimate parameters under robustness? And thank you.
Do you have one or two questions for Jayadev? Yeah.
Oh, where does the 1 over 60 come on the bound for gamma?
Okay, so you see those 1 minus 9 gamma and those things, when we try to deal with them, our computations become very simple. So we believe that if you should be able to go very close to a half. But for many of these computations to become nice, we have just 1 over 60 is something that made our computation just go through. It's not a hard threshold. In fact, one of the versions that we are thinking is, what if gamma is really large, then what can you say? So for example, I think if you do not care about an efficient algorithm, then we can make gamma very close to half.
Further questions? Okay, since we're running a little late, I think we'll go ahead and thank the speakers for the session one more time and head to lunch. So thank you, Jayadev.
Yeah.
And we are back at 2 p.m. So you have a nice long lunch break. See you all then.